Yeah, so thanks for watching this video. I'll be going over some of my answers to the AP report questions, as well as the paper that's in progress and some updates on my PhD work. Yep, so we have an outline here of the main objectives. First, we'll be going over my answers to the first AP question, the paper discussion, that is in progress and how it relates then to AP question 1 and the connections that we can see in between them. And then we'll be going over the second AP question, and then lastly going over some updates on my PhD project status. Yep, so looking at the first AP question, the first part of the first question begins with the setup of an updraft without entrainment, where entrainment equals 0, and there are no exchanges occurring with the free troposphere. And the question was, how does the free troposphere's humidity impact the buoyancy? With the equations you can see here on the right, we have the saturated MSC of the plumes change with height is equal to minus the rate of entrainment times the saturated MSC of the plume minus the regular MSC of the environment. And so in this situation, thinking purely just in terms of equations, we know here that our entrainment rate is 0, we plug that into our equation above, and we end up with a rate of change with height equal to 0, where under this assumption we can infer then that the environment's specific humidity is not going to be impacting the plume's saturated MSC, and thus it will not be impacting the buoyancy. Here I show the same idea. We're still looking at part 1, the non-entraining plume, but now we're looking at this in terms of a figure, where on the x-axis we have here is moist static energy, and then here we have the height. And so the blue line is the regular MSC of the environment, the green line here is the saturated MSC of the environment, and then this purple line right here is the saturated MSC of our plume without entrainment. And so we can see here that under non-entraining, our parcel, once it hits the level of free convection here, its MSC is going to remain constant through the full column. And so once we are out of the boundary layer and above the level of free convection, like I've said here, our environmental specific humidity is not going to be exerting any impacts then on the amount of buoyancy, which can be inferred by this area here between the saturated MSC of the plume and then the saturated MSC of the environment. For part 2 of question 1, we now have a setup where we are including entrainment, and the temperature is going to be the same for the environment and the plume, and the relative humidity remains constant through the whole profile. And the question for this part was, where will entrainment exert the greatest updraft dilution? And so same idea as before, where we have MSC on the x-axis and then height on the y-axis. Blue is environmental MSC, green is saturated environmental MSC, but now when we're considering entrainment, we're looking now at these black lines, which are the saturated MSC of our plumes when you include entrainment. And these different black lines represent different rates of entrainment, where here on this side, you're seeing entrainment rates that are smaller, and then entrainment rates increase as you continue down these lines. So now to kind of go over some of this discussion, I recreated this figure. Same idea, MSC on the x-axis, height on the y-axis. Blue is our environmental MSC, green is the environmental saturated MSC. And now I've drawn in a black line of an entraining plume. So this is the saturated MSC of an entraining plume. And then this purple one is a callback to the first part of the saturated MSC of a non-entraining plume here. And so when we include it, we're now incorporating relatively cooler and drier air from the environment into the plume, and this is going to really act to impact the plume's saturated MSC. and we're going to see a subsequent reduction in buoyancy. So what we consider to be buoyancy is the area between the saturated plumes, MSC, right here, and the environment saturated MSC. So first, when we're considering a non-entraining plume, we see this area is much greater, right? So we're going to see a much larger buoyancy potential for this profile. But when you are including entrainment, you instead see a much smaller amount. And so we can show you here, I've colored in the difference then between the non-entraining plume profile and then the entraining plumes profile. And it's this difference that really gives us an idea of the amount of updraft dilution that is occurring. And so under a constant entraining rate, which is approximately what I've drawn in here, we can see that further left in the troposphere, we see a much larger deficit occurring between the non-entraining and entraining plume versus much lower in the lower free troposphere, and even further down, this is significantly smaller than it is further aloft. And so the answer for this part of our question is that entrainment is exerting a stronger diluting effect aloft in the middle to upper free troposphere up here. So now I'm continuing on to parts 3 and 4 of AP question number 1. Part 3 asked about how applicable the two scenarios of an entraining plume and a non-entraining plume are in the tropics. And my answer can essentially be boiled down to this, where Zipser in his 2003 paper really emphasized the rarity of undiluted convective towers in the tropics. Executing an intensive observational analysis, he showed that the second scenario, where you have an entraining plume, is more realistic in the tropics. And while non-entraining plumes may be possible and present in mid-latitude storms, we're just not really seeing enough undilute updrafts present in the tropics, especially over the oceans, to account for the amount of enhanced values of MSC observed at the tropopause. So instead, many of the hot towers that Zipser's paper goes over showed a notable amount of entrainment, especially in the boundary layer and the lower free troposphere. Part 4 then asked about some of the complications present in modeling convection and entrainment in the tropics. And current research is showing that many current models struggle to accurately represent moisture thermodynamics with an overly dry lower troposphere that leads to deficiencies in simulating the dynamics of convection and turbulent mixing. And so what the models are showing is that is a stronger near-surface mixing than what is really observed. This acts to weaken the vertical moisture gradient, and that makes the modeled surface a lot drier than what observations actually show. The model then often fails to allow convection to entrain environmental air. And given that undiluted convective cores are extremely rare, as noted in the applicability to the tropics, part 3, we see that this misrepresentation leads to inaccuracies in simulating systems characterized by tropical deep convection, such as those like the MJO. Okay, so now I'm going to move on to the second part of this presentation, and that's going to be a discussion on the paper and its ties to my first AP question answers that I just went over. Broadly, these are some of the really key figures from our paper that's in progress. And I cover the trends in these and the theory, the plume buoyancy theory underlying them, especially the equations that we use to compute the plume buoyancy and its decomposed components in my tropical presentation. And so I'm not going to be going over that now in this presentation. And you should all have access to my tropical presentation. And if you don't, please let me know and I will get that to you. But now, instead, I just want to quickly kind of go over how it can be related to the first AP report question, and just kind of how can we infer the MSC evolutions in the profiles and composites of tropical mesoscale convective systems through their lifetimes. And so to quickly orient everyone on these figures, on the left here we have the decomposed plume buoyancy for the 3 stages of the MCS life cycle. So stage 1 is growth, stage 2 maturity, stage 3 decay. And on the top row here, this is our total plume buoyancy anomaly. Second row is undiluted component, and third row is the diluted component. Rows 2 and 3 that we add together to get then the total plume buoyancy, which is the top row there. And then on the right, these are vertical profiles of our composites, like taken across like this. And so on top we have temperature anomalies, and the bottom is specific humidity anomalies. And the black contour lines are the same for both figures, and those are vertical velocities, where solid contour lines indicate upward movement and dashed lines indicate downward movement. And for all of these figures, so like all of the data, including vertical velocity, temperature, specific humidity, buoyancy breakdown, all of these are anomalies relative to the spatial and temporal means. So, just to start out, I will be covering over MSE equation and the saturated MSE equation, and how it's used to compute the different parts of the plume buoyancy breakdown. So regular moist static energy can be interpreted as the combination of inherent energy, latent heat potential, and then geopotential, whereas saturated MSE is, again, still inherent energy and geopotential, but now it's our latent heat potential considering a specific humidity where the air is saturated. And that's the main difference between these two. We use these two quantities for different layers of the lower troposphere to get a better understanding of the buoyancy components. Our undilute component here, row 2, is calculated by taking the regular MSE of the boundary layer minus the saturated MSE of the lower free troposphere, all divided by the saturated MSE of the lower troposphere. And then our diluted component, row number 3 here, is calculated by taking saturated MSE of the lower free troposphere minus the regular MSE of the lower free troposphere, and dividing all of that again by the saturated MSE of the lower troposphere. And so for the work in our paper, we defined the boundary layer as the surface to 850 hectopascals, so like right here, and then the boundary layer as 850 to 600 hectopascals, like right here. Now, I want to consider how these components can really combine. Temperature, specific humidity are considered in terms of moist static energy to make the figures that we can see here on the left. For stage 1, we can see here that stage 1 is dominated by our undilute component, as we can see here. When we add these together, we're still ending up with an overall positive buoyancy anomaly, and this can be contributed then to like the really dominant undilute component. And this is reflected by the very warm, very moist boundary layer, meaning that we're going to have a really large regular MSE of the boundary layer. That's not to discredit, we see in the lower free troposphere that it is still warm, but now instead dry further aloft. It is in this situation that we can really see that our buoyancy is going to be really concentrated in the lower troposphere. We having bottom heavy buoyancy during MCS growth. And then, so in stage 2, we don't really see anything that crazy, and it's kind of what we anticipated. And you can see here that the undilute component and the dilute component are added together, and they almost nearly are canceling one another out. Not that their anomalies are that strong to begin with. And so this is reflected when we look at our mean profiles. I mean, the anomalies for both temperature and specific humidity through the full columns are also just near mean values. But we see a big change when we move on now to stage 3 of storm decay. Again, we're still seeing that this undilute component is really acting to strongly influence the overall total plume buoyancy, right? So adding these together to get our total plume buoyancy, we're still seeing that the overall center of the composites is largely a negative anomaly. This can be seen then from the really strong cold and dry anomalies that are observed in the boundary layer, and we can see that the lower free troposphere and the middle free troposphere, so further aloft up here, above here, so above the green circles, we're still seeing they're still cool and moist. This is still, we can see this as it's reflected as actually a part of the positive contribution to total buoyancy from our dilute component, which is just an interesting little tidbit there, that we see this kind of like reversing action of dilution really playing a dampening role in MCS growth versus a strengthening role in stage 3 or storm decay, and then vice versa for the undilute component, where again the undilute component is the predominating component of the total plume buoyancy. Okay, so now I'll be moving on to my second AP report question. And so this one really focused more so on deep convection's microphysics, some of the theories behind it, and ways that we've measured it, and some of the concepts that have arisen to be really important in this area. So first, I want to go over the original hypothesis on aerosol impacts in convection. So this original hypothesis was really championed by Rosenthal et al. In 2008, and they dubbed this the cold phase aerosol invigoration theory. Relies on the idea that in a scenario, if you have fewer aerosols present, i.e. less pollution, you have less available particles to act as cloud condensation nuclei. Without as many nuclei, less droplets are created, but that also means that these droplets are larger in size. Larger drops are able to quickly rain out, meaning only a very small amount of the condensed water is actually able to make it past the freezing point, where then less latent heat release occurs than otherwise. In turn, this meant that the theorized heavy pollution meant more cloud condensation nuclei, smaller drops, and a latent heat release that was enhanced. And so overall, this theory just boils down to saying that deep convection was more likely in polluted environments. However, this theory has a lot of drawbacks and arguments against it. Warm phase invigoration. And so this relies really heavily on the idea that higher aerosol concentrations and higher cloud droplet concentrations mean there's a faster condensation and lower supersaturation requirements. This means that latent heat release is increasing, and that acts to really boost buoyancy. In the paper by Eigel and Van de Hever 2021, they showed that assumptions for cold phase aerosol invigoration are unrealistic, including instantaneous freezing and then fallout of hydrometeors. Studies have only shown that warm phase processes have seen invigoration. And this was only then when we involved modifying the moist adiabatic lapse rate calculations in order to include freezing, supersaturation, and condensate loading. There's a large caveat with these studies where the calculations and modeling were conducted utilizing parcel theory. In the tropics, right, this parcel theory just isn't sufficient to accurately and fully describe tropical deep convection. We also see in a paper by Peters et al. 2023, they utilized observations showing how moderately polluted undilute parcels experienced a slight invigoration, while strongly polluted parcels were instead starkly weakened. The moderate pollution had more contributions from the condensate loading and latent heat, and temperatures below -4 degrees Celsius saw loss of water vapor by entrainment. These were overridden by contributions to the buoyancy from condensation and the freezing latent heat release. Consequently, heavily polluted parcels instead saw decreases in heat capacity, where lost water meant that the parcel cooled at a faster rate with height. Warmer polluted parcels experienced latent cooling via entrainment at a faster rate than the cooler, clean parcels. And this comes about as a consequence then of positive scaling between the dilution rate and a parcel's excess temperature. This is to say that overall, cold phase aerosol invigoration really isn't the most appropriate, and so then that kind of brings us around to the last main point of this research question, and that was applications to tropical deep convection, and then how we can use radars to better understand some of these relationships. In the tropics, we see a greater sensitivity and a larger condensate loading, which then leads to a more pronounced pollution impacts when compared to mid-latitude convection. And so we know that the tropics are super under-observed. And while planes might provide the most accurate info, they are very expensive and severely limited in spatial and temporal scope, especially when we're trying to consider these convective cycles at more extended lengths of like a full MCS's lifetime. We also see that the controls of cloud formation processes are on the micrometer scale, and that also makes it really difficult then to observe with traditional remote sensing, i.e. satellites, which works at a much coarser scale. We can use radar reflectivity and the liquid-water content relation to infer entrainment rates, and that's that Z is equal to the A times the liquid water content risen to the power of B. This shows that a positive correlation between the exponent B and the homogeneous mixing degree. Overall, we really see the importance then of obtaining further in situ observations of the tropics and tropical deep convection, both in terms of better understanding how we can improve our measurements using tools such as like radar reflectivity, but then also how can we use this information to better inform models and forecasting and how we understand the base processes underlying tropical deep convection. I'll be going on to the current status of my current PhD project. I would like to analyze lightning as a convective proxy, and then also any links that we can research between hydrometer currents and then the mesoscale convective system life cycle in the tropics. In this first topic of trying to see if we can utilize lightning as a convection proxy, previous researchers have used things such as like the Worldwide Lightning Locator Network, WLIN, to track MCSs and to even identify rapid intensification in systems such as like tropical cyclones. Other research is Sarah Bang's work, kind of looking into some of these differences that we see in lightning occurrence in oceanic originating convection versus land originating convection. Remote means have definitely improved, enough to the point that I think we can start potentially shifting this analysis into seeing how we can use upper atmospheric lightning, as they're known in the literature as transient luminous events, or TLEs. I think we can start trying to see if there are any observable connections to tropical deep convection. And current research has really mostly focused on connections between TLEs to tropical cyclone intensification and oceanic convection. I can talk more about this later, but I think there's something really exciting and promising in this area. And then the second main topic, kind of where I kind of would like to see maybe how we can start analyzing connections between buoyancy and hydrometer collisions, and seeing how hydrometer count and size and distribution through these plumes under these different modes of buoyancy change throughout the life cycle of a mesoscale convective system, and its connections then to both lightning occurrence and then the TLE occurrence. And really, this is all just very intertwined and I think very exciting. And I look forward to the questions I'll be getting in response. Thank you.